Hello, class. I'm going to take the last part of this lecture to introduce Black's formula. And Black's formula is a pricing formula for options on futures or forward contracts. Now, for the purpose of deriving the Black's formula, I'm not going to make any distinction between a forward contract and a futures contract. So essentially, I'm going to treat them as if they're the same product, ignoring the minute structural difference between those two contracts, provided they have the same expiry date. So if a forward contract and a futures contract have the same expiry date, I'm just going to treat them as if they're the same. So, and for the rest of the lecture, I'm going to just make reference to forward contracts. And you should be understand that whatever I say for forward contract applies the same way for futures contract as well, for the purpose of deriving Black's formula. Now, suppose we have a forward contract that follows a log normal process like this. And we have a derivative contract that has the forward contract as the underlying asset. And the forward contract and the derivative contract, they both have the same expiry date. Now, in this case, by Ito's lemma, the derivative contract will follow this particular process here, which we have seen many times. Now, to derive Black's formula, we can take the same approach as we have taken before. So we will construct a risk-free portfolio. And the construction will be very similar. So we'll take delta units of the forward contract, and we're going to short 1 unit of the derivative contract here. Now, the forward contract, F, will have an initial value V0. Now, for a stock, the price of the stock and the value of the stock per unit they're the same, right? If a stock is worth $100, then the value of that unit of stock is $100. But this is not the case for a forward contract. For a forward contract, you have a forward price of 100. The forward contract is actually designed in such a way that the initial price is set in such a way that the initial value of the forward contract is 0. Okay, so same thing is for the futures contract. So the futures price is set in such a way that the initial price of the futures contract will have a value of 0. Okay, so the value and the price of the forward contract are different. Now, the price, the portfolio is constructed in such a way, and the portfolio the value of the portfolio will change in this form here. Now, the blue one is really the change of the price of the derivative contract. And here is really a change of the price of the value due to the change of the price of the forward contract here. Now, because it's deterministic, then the portfolio must grow at the rate of risk-free rate. Now, the initial value of the forward contract is 0. So the value of this portfolio really is just the value of minus F here. Now, if you plug in that, you'll see the change of the portfolio is taking this particular form, which is equal to minus RF dt. And you have derived a partial differential equation here. Now, if we look at this one here, and this one has a very similar form as the one that we have seen earlier, a partial differential equation for options on stocks, provided that if the rate of for that stock is paying a continuous dividend yield equal to R. Now, because here, there's another term for that. So if you look at it earlier, that the partial differential equation for a stock that derivative on a stock that pays dividends has this R minus Q term here. Now, if Q is equal to R, this entire term dropped out. So we're left with this and this equal to RF, which is really this form here. So you can think of a futures contract. The PDE associated with the futures contract is really the same as a PDE associated with the stock as an underlying asset, where the stock pays a dividend yield that's equal to the risk-free rate R. Now, solving that partial differential equation with the boundary condition, where in this case, the boundary condition is for a stock, for a call will be F minus K, and F at maturity would just be the stock price at maturity of the forward contract. The spot price of the stock at the maturity time of the forward contract. So you then have a form here. So again, if you look at it, this is very similar to what we have seen before on the Black-Scholes-Merton formula. If you change S to F, and if you plug in Q equal to R, then essentially you will have a formula here. Okay, now because forward contract does not pay any dividends, so it's for a options on futures, you really don't have to worry about dividends. So there's only one form for this formula, and that's you don't have to have, like before we have basically something that for a stock doesn't pay dividend, and then we expand it to stock that pays dividend. Here, by the nature of the underlying asset, there's no dividend payment. All right, so I'm going to stop the lecture here.